Hello everyone, this is part 2 of the consistent mass matrix derivation of a bar element. So in case if you have not watched part 1 of this video, I highly recommend that you go back and watch part 1 of this video. I will give the link in the description below. So just a recapitulation of what we did in part 1, we took a cantilever bar and we were able to derive the governing differential equation by using Newton's second law. We were able to derive the governing differential equation. You can see the Newton's second law here, and we were able to write the force in terms of stress and stress in terms of strain. And on the right hand side, you were able to write the mass in terms of density, and acceleration is d squared u by dt squared. So that's our governing differential equation of the longitudinal vibration of a bar. Now, in this governing differential equation, a governing differential equation is nothing but the residual. If you have a residual, you can use Galerkin's weighted residual method, which is integral of weighing function. You hit you hit the residual by the weighing function and equate it to 0. Integrate and equate it to 0. Well, when you do that, you have already completed what for the left hand side. You have already completed that for the left hand side, and we have to do the weak form for the right hand side. So what I'm going to do is I'm going to feed the values of the shape functions for the right hand side, and hopefully I can get the mass matrix if I do the mathematics precisely. So let me do that. Okay, this is the term. Now, by convention, there is no difference between weighing function and shape functions. Shape functions are denoted by the notation n suffix I. There can be more than one shape function, but in our case, we have two shape functions. I will represent that. N1 is 1 minus x over L, and N2, it is x over L. Shape functions are nothing but the trial solution with the constants removed. So what is our solution? The displacement at any point in space and at a particular instant of time is given by 1 minus x over L into u1, which is the displacement of the nodal point 1, which is of course the function of time because it's vibrating, plus x over L into u2, which is a function of time since it is vibrating. Now, all I'm going to do is I'm going to find the value of d squared u by dt squared. So it's very simple. Let me rewrite this equation u of x comma t. Let me rewrite that equation as n1 u1 plus n2 u2 so that I can do the mathematics in a very, very conducive way. Now, tell me what is du, or you may want to call that as dou u, partially differentiate that with respect to time, specifically with respect to time. So you are going to get n1, which is not a function of time, into dou u1 by dou t, plus n2 into dou u2 by dou t. Since u1 and u2 are functions of time, I'm just differentiating them with respect to time. I can find what is dou square u over dou t square. That is simple. It is n1 into dou square u1 over dou t square plus n2 into dou square u2 over dou t square. All right. Now I have the expression for dou squared u over dou t squared. All I have to do is take it and plug it here. Mathematics is just like moving objects. So before I do that, in order to make sure that mathematics is going to be even more conducive, dou squared u by dou t squared can be represented as n1 into u1 double dot, which means I'm differentiating that u1 with respect to time 2 times, plus n2 into u2 double dot. If I do that, I'll be getting integral of ni into n1 into u1 double dot plus n2 into u2 double dot into dx. Now we have two shape functions. So what I'm going to do is I'm going to let I is equal to 1. If I let I is equal to 1, then ni becomes n1. So it becomes n1 into n1 into u1 double dot plus n2 into u2 double dot into dx. Of course, I'm integrating over the limits over the entire length of the small piece of the bar. Small piece of the bar, that's what I'm doing. So in the next step, I'm going to hit this equation by n1. So what I get is, I get integral over the limit 0 to L. It becomes n1 square into u1 double dot plus n2 square, I'm sorry, it's a n1 into u2 double dot into dx. That is right. So all I have to do is I have to substitute the values of n1 and n2 here. So let me substitute the values of n1 and n2. n1 square is demanded in the equation, and also n1 into n2 is demanded. So let me do that. The next step is integral over the limit 0 to L n1 squared. n1 is 1 minus x by L. So it's of the form a minus b the whole square. It's a square plus b square minus 2ab. That is n1 square. Okay, that is n1 square into u1 double dot plus n1 into n2. n1 is 1 minus x over L, n2 is x over L, so I get x over L minus x square over L square. If I multiply n1 and n2, that's what I get. Into u2 double dot, that is a double dot, I'm sorry. So I will use a different color to represent that. Okay, that's a double dot. And I'm going to integrate the entire term with respect to x. So in the next step, what I'm going to do is I'm going to integrate and substitute the limits directly. So if I integrate and substitute the limits directly, so I'll be getting, if I integrate 1, I get x, and if I substitute the limits, I get L, upper limit and lower limit. If I substitute the lower limit, it becomes 0. So let me not bother about the lower limit. Plus x cubed by 3L squared. So that becomes L over 3 minus this becomes x squared by 2. So that becomes L into u1 double dot. What I'm doing is I'm integrating and substituting the limits directly. That's right. Plus, if I integrate and substitute the limits directly, I get L over 2 minus L over 3 into u2 double dot. The next step is L by 3 into u1 double dot plus, if I take the LCM, I get L by 6 into u2 double dot. Okay, all right. So this is going to be our equation number 1. This equation we got by putting I is equal to 1, which means ni becomes n1. By fitting the first shape function, I get this equation. Now all I have to do is I'm going to feed the second equation so that I can get the second equation. So second shape function, I'm sorry. So feed the second shape function in this equation here. So when you put I is equal to 2, what happens to this equation? It becomes, the next page, the equation becomes integral over the limit n2 into n1 into u1 double dot plus n2 into u2 double dot with respect to dx. Of course, you are going to integrate over the limit 0 to L, and if you hit this equation with n2, you are going to get integral over the limit 0 to L n1 into n2 into u1 double dot plus n2 square into u2 double dot with respect to dx. So what is n1 times n2? Integral over the limit 0 to L. n1 is 1 minus x by L, n2 is x by L, so it becomes x by L minus x square over L square into u1 double dot plus n2 square is x square over L square into u2 double dot. Of course, you are going to integrate this with respect to dx. Integrate the whole term with respect to dx. So in the next step, I'm going to integrate and substitute the limits directly. So I get L by 2 minus L cube by 3 if I integrate and substitute the limits directly into u1 double dot plus, if I integrate and substitute the limits directly, I get L cube divided by 3 into u2 double dot. I'm sorry, I think I'm making a terrible mistake here. It's a terrible mistake. Okay, if I integrate and substitute the limits directly, so what I get is I get L over 2 minus L over 3, because the L cube in the numerator and the L square in the denominator, they cancel out. So you are left with L in the numerator into u1 double dot plus, again it's L over 3 into u2 double dot. And that's the double dot again. So here, if you take the LCM, you get L over 6 into u1 double dot plus L over 3 into u2 double dot. Now this is equation number 2. Now I'm going to write the first and the second equation in the form of a matrix. If I write the first and the second equation in the form of a matrix, where is the first equation? So our first equation is L by 3 into u1 double dot, that is double dot, plus L by 6 into u2 double dot. That's our first equation. The second equation is L by 6 into u1 double dot plus L by 3 into u2 double dot. That's our second equation. The way you write the two equations in matrix form, it's very easy. So okay, you first write the coefficients of u1 double dot. What is the coefficient of u1 double dot in the first equation? It's L by 3. Then what is the coefficient of u2 double dot in the first equation? It's L by 6. What is the coefficient of u1 double dot in the second equation? It's L by 6. And here, what is the coefficient of u2 double dot in the second equation? It's L by 3. Now I can take L by 6 common outside. If I take L by 6 as a common term outside the matrix, I get 2, 1, 1, 2 into u1 double dot into u2 double dot. Now what happened to those terms here? The rho A, I missed this rho A. In every term I have to include this rho A. I missed that. I'm terribly sorry about that. So all I have to do is include this rho A, which is a constant I missed. So every term, don't forget this rho A. It's an excuse, I'm sorry. So that's right. So you get rho A. This is a common for equation 1. And also rho A is going to be common for equation number 2. That's right, rho A. Okay, it's a rho A. That's right. And now you get a rho A here, you get a rho A here, you get a rho A here. It's a rho A L over 6. So this term, rho A L over 6, 2, 1, 1, 2, this is our consistent mass matrix. Now, we operated, let us go back to the weak form of this equation, the governing differential equation. We operated on this term to get what? To get this equation. To get, okay, here we go. To get this equation. And we operated on the right side term, on this guy to get the mass matrix, consistent mass matrix.